Hello everyone, my name is William Moreno, and today I'm going to talk to you about integrated solar thermochemical reaction systems. But before I do that, as requested by Dr. Valentine, let me talk to you a little bit about who I am and what is it that I do. Alright, so a little bit about me. I'm a wartime vet. I served under the U.S. Army Reserves, attached to the 1st Armored Division, and we were deployed to Iraq between March 2003 till May 2004. I'm an electrical engineer with a bachelor's in science in electrical engineering from the Polytechnic University of Puerto Rico. I got my degree in 2001, got my PE license from California a few years ago, and I've also been a certified energy manager since 2010. Now, I only need two more classes to get my master's degree in sustainable energy engineering from University of Maryland. Currently working for NAFAC Southwest in San Diego, California. Been working here for the last 10 years in capital improvement projects, which are mostly facilities like admin buildings, piers, hangars, and lately a bunch of those hangars have been for the new fighter jet, the Joint Strike Fighter. All right, one of the interesting projects that I've worked during my tenure at NAFAC was a natural gas power plant that we built at 29 Palms in 2010. It's a $50 million design build power plant with a 9.2 megawatt electrical capacity at 12.7 kV. Connected to an existing power plant that generates 7 megawatts and also connected to a 1 megawatt PV array. And we're also connected to the grid, so it's not an isolated plant. The plant uses natural gas as a fuel source to feed two 4.6 megawatt combustion turbines by solar turbines. And we use the heat from the turbines exhaust to feed two 1,300 tons absorption chillers to produce chilled water for cooling, and also feed two heat recovery boilers to produce high temperature hot water for heating. As a supplement to the heat recovery boilers, we also have installed two 50 million BTU hot water boilers for high temperature hot water production. The plant uses natural gas as the main fuel source, and the backup fuel is LPG. And we also install an on-site storage for the LPG, in the order of 250,000 gallons. These turbines can be swing loaded from 50% to 100% load, depending on what is the load condition on the base. And they only produce 5 particles per million of NOx from 50% to 100% loading, which makes them very, very, very one of the cleanest turbines that you can find on the market without after stack catalytic converter. The turbine model is Mercury 50. You can look at them on their solar website, solar turbines website. They're very impressive machines indeed. Well, enough of that. Now you guys can see here another shot of the back of the plant, where we can see the heat recovery boilers installed right next to the stack of the plants. And the previous shot that you guys saw were of the inside of the plant where the two turbines are installed currently. Well, now let's talk a little bit about the assigned project that I have. And here's a little bit small overview of what the project is about. The project was awarded to Pacific Northwest Laboratory. These guys are located in Washington. The project had a start date of February 19, 2013, with an award amount of roughly $3.5 million. The project has an estimated duration of about 2 years. So the goals of the project, goals and objectives. Now the goal of the project is to advance the technology of solar thermochemical reaction systems to achieve a levelized cost of electricity no greater than 6 cents per kilowatt hour. Now we all pretty much have this common goal, which is from DOE, the mandated from DOE, or the goal from DOE to discover or advance technologies to the point where they can achieve 6 cents a kilowatt hour by 2020 in order to compete with other power producing technologies. Now the objectives of this project are to improve the performance of the solar thermochemical reaction system, increase the solar to chemical energy conversion efficiency from 63%, which is where their system is currently at, and they achieved that on a previous project that was funded by American Recovery and Reinvestment Act in 2009. Improve it from 63% to 74-75%. Increase the solar thermochemical augmentation from about 20% to as much as 28-30%. Now this is in terms of the high heating value of the methane. That's what it is. Also, they want to reduce the manufactured cost for critical components, which are the reactors and the heat exchangers, and perform an end-to-end demonstration using a combustion gas turbine. Now let's talk a little bit about the system approach and how the system is and how is it that it works. Okay. Well, water and methane, in principle, are preheated and then reacted in a steam reforming reactor that is heated by concentrated solar energy from a parabolic dish concentrator. The product stream, which is syngas, and with a 20 to 30% higher energy content than regular methane, is then fed to a combustion cycle power plant for electricity production. And that's the image here on the screen is simplified version of what is it that the system does. Simple enough, right? Well, let's go a little bit more in detail in the actual process and see what happens inside the solar thermochemical reactor. Well, each stream, which is water and methane, they're actually, they're initially preheated to a couple of counterflow microchannel recuperative heat exchangers, which are heated by the exhaust stream of the reforming reactor. Then the steam and the methane are mixed before entering the high temperature recuperator, where the combined stream is further preheated to a temperature that is close to the operating temperature of the reforming reactor. The combined and preheated stream then enters the reforming reactor, where the mixture passes over a methane steam reforming catalyst, absorbs solar heat at temperatures up to approximately 850 degrees Celsius, and it is converted to syngas according to the methane reforming reaction and water gas shift reaction equation that we see on the right hand side of the screen. Okay, well, from there, syngas, we already have syngas, and the syngas is cooled down through several methane and water preheaters that were described earlier, and then through a radiator, and lastly, flows through a vapor liquid separator where the condensed water is removed. Then at that point, the syngas is relatively dry and is ready to be used in a combustion turbine generator. Or if syngas, generation is higher than the demand, it can be stored, for later use. Okay. So benefits of the system. For starters, doesn't look to displace fossil fuels, which is somewhat can make it more attractive to some investors with interest in fossil fuels. It is only looking into doing augmentation of the energy content of natural gas, so it can be relatively easy to retrofit into existing power plants. Now, this can be of very, very great attractive to utility companies that depend on buying natural gas from other companies, and as this can be a direct savings to them in the O&M of the plant by reducing their fuel consumption by at least 20%. Another benefit is that the system works 24 hours a day versus other solar systems like photovoltaics. When the sun is down, the power plant can completely bypass the concentrators and use CH4, methane natural gas directly. Or if the project chooses to have storage for syngas, then you can use the syngas that you store at night and during nighttime when the sun is not up. And this can, in fact, this in return can turn your to a high capacity factor of 90% or over, depending on the storage options that you choose. The system also reduces the plant's CO2 emissions. If you use 20 to 30% less fuel, then you will reduce the emissions at least by that amount. Also, testing. Now, the team had initially three tests that they want to do during this initial test. They were not planning to do a cloud cover, but they run into that during the testing, so the results are posted there as well in that image that we see on the screen. But for steam reforming, they they were planning three solar operating conditions. And one condition, the first condition was with a screen placed in front of the aperture to block roughly half of the solar flux, and they call this screen condition. And the second condition was with the with the dish, and with the dish was moved in a circular motion to what they refer to as spill a portion of the solar flux away from the aperture, and they refer this as circle tracking. And then the third was where complete solar flux was directed into the aperture of the receiver, which they call full sun. Now with with the solar screen, the methane conversion reached roughly 50%, not so great. And now with the using the circle tracking mode, the methane conversion reached as high as 75%, which is much better. Now with the direct sun, with this setting, the methane conversion exceed 90%, which is what we see on the upper red dots on the right hand side of the image there. Pretty impressive. Then lastly, they have tree shadow. They tried tree shadow, but by that time it was pretty much the end of the day, and the solar radiation was pretty much gone. So not very relevant data to show there. Accomplishment and issues. Now there was a report on April 15, 2013, and the project team reportedly achieved that they have reached 6.5 cents per kilowatt hour for levelized cost of electricity, which is very close to the target goal. But again, they have worked in this project before through a separate project in 2009, as I mentioned earlier. So they already have some progress on that arena. But 6.5 cents is pretty close to the target, which is pretty impressive. They also set up a solar concentrator test stand on their site in order to conduct further testing. And if you look at the report online, you'll see the photos, which shows that they actually did it. So they also list some planned milestones, which is to do the commissioning of that solar concentrator test stand by June 14, 2013, and start testing on the durability of the catalyst, to determine how long will it stand or last during continuous use at such high temperatures. Also, they were planning to start developing initial baseline bottoms-up equipment costs and down selecting manufacturing processes to include in equipment cost modeling tools. However, none of this was reported, whether or not it was done. No further updates were found after this report of April 15. The next report should have been submitted by the end of the second quarter of the calendar year 2013, which ended in June 30. Since no further updates have been found since April 15, and it's been more than a year since the last update, obviously something wrong was going on. Now I found out that one of the major barriers that the team may have faced was the filing for bankruptcy of Infinia Corporation. Infinia Corporation is the company that fabricates the solar dish that the team choose to use in their prototype. So obviously, and they've been working with this company for a while from the past project. So this was obviously a big blow on for them. So if they depend on those dishes, then now they have to find some new dishes and retrofit or adjust the system to use that new dish. So in conclusion, the system has a lot of potential. I think that the DOE goal of 6 cents a kilowatt hour could be easily reached, since they are already really close to the target. However, the long-term durability is still yet to be proven, in my opinion, on the overall reactor assembly and in the catalyst. For some reason, the catalyst material was not listed anywhere. I couldn't find it in the patent that they filed, couldn't find it in any of the reports and any of the Word documents. But I'm thinking that it could be either nickel or rubidium. I think that the O&M can be an issue in the reactor, since it will be subject to 850 degrees Celsius on a pretty continuous basis. But maybe not, since they build it out of Haynes to 30 alloy, which is an alloy that is commercially available and already been tested to withstand very high temperatures. If you Google alloy, Haynes to 30 alloy, you'll find the catalog, and it shows a bunch of data there. So it's been around for some time. but I'm not sure. I couldn't find any data that tells me that they have used that type of alloy in this type of application. So again, it could be an issue also. Well, but maybe not. Another issue will be the real estate. If you want to install these dishes on an existing power plant, you'll need land close to that power plant to put the dishes around. I found some data that the Pacific Northwest Laboratory team, as a rough number, says that, for example, if you have a 500 megawatt power plant, you'll need about 3,000 dishes to augment that the natural gas that that plant uses. That's a lot of dishes, and therefore a lot of land. But again, I don't see any of these issues to be real showstoppers. Power plants normally they use big pieces of land, so hopefully they'll find some. They'll have some land nearby. Um, no real showstoppers here. So I see the project moving forward, and I see that it could easily be implemented in the near future. So. Well, that's about it. For further information, feel free to send me an email if you want to get more info about the project. There's a lot of more data that we couldn't cover here due to the small time that we have available. So thank you very much for your attention and have a nice day. Thanks.